Hello, my name is Jeremie Kim, and I'll be presenting our work, Revisiting RowHammer, an experimental analysis of modern devices and mitigation techniques. I'll first begin with an executive summary. Denser DRAM chips are more vulnerable to RowHammer, but there is no characterization-based study that demonstrates how exactly the vulnerability scales. The problem is that it is unclear whether current mitigation mechanisms will remain viable for future DRAM chips that are likely to be more vulnerable to RowHammer. The goal of this work is to first experimentally demonstrate how vulnerable modern DRAM chips are to RowHammer and study how this vulnerability will scale going forward. Secondly, we want to study the viability of current mitigation mechanisms on more vulnerable chips. We are the first experimental study to present a rigorous RowHammer failure characterization study across a broad range of DRAM chips. We characterize over 1,500 DRAM chips across different DRAM types and technology node generations across the three major DRAM manufacturers, and we demonstrate that the RowHammer vulnerability worsens in newer chips. We also study RowHammer mitigation mechanisms in simulation and show how 5 state-of-the-art mechanisms are affected by a worsening RowHammer vulnerability. We find that these mitigation mechanisms have reasonable performance loss on modern DRAM chips, but scale poorly to more vulnerable DRAM chips. We conclude that it is critical to research more effective solutions to RowHammer for future DRAM chips that will likely be even more vulnerable to RowHammer. Here is the outline for the talk today. I'll begin with a brief introduction of the RowHammer phenomenon. In order to access data from a DRAM row, say row 2, the memory controller must first open or activate the row. After all requests are serviced from row 2, the memory controller must close or precharge the row in order to begin accessing data from another row. Due to an increase in cell-to-cell interference as a likely result of increased cell packing density, rapidly activating and precharging a DRAM row can result in bit flips in nearby rows. Continuing to access the same row results in even more failures in nearby rows, and this phenomenon is known as RowHammer. We refer to the rapidly accessed row as an aggressor row, and the rows containing bit flips as victim rows. I will now discuss the DRAM background in the context of RowHammer bit flips and how they occur. DRAM is comprised of an array of cells that store data as charge and are organized into rows. Each cell encodes data in fundamentally leaky capacitors. Here is a simplified diagram of a DRAM cell where the capacitor in red stores the data and the access transistor gates access to the data. There are a number of leakage paths by which charge can enter or exit the capacitor. The important thing to note is that stored data can be corrupted if too much charge leaks, which is the same as saying if the capacitor voltage degrades too much. Each cell encodes data in fundamentally leaky capacitors. Here's a simplified diagram of a DRAM cell where the capacitor in red stores the data and the access transistor gates access to the data. There are a number of leakage paths by which charge can enter or exit the capacitor. The important thing to note is that stored data can be corrupted if too much charge leaks, which is the same as saying if the capacitor voltage degrades too much. Here we have a simplified diagram of the capacitor voltage over time. We see that the voltage decreases over time in an exponential decay. There's a threshold Vmin under which we can no longer guarantee that we will correctly read the data that was originally stored in the cell. As long as the cell's voltage remains above this line, we consider this a retention success. However, as soon as the voltage drops below Vmin, we consider this a retention failure. In order to prevent failures from charge leakage known as retention failures, periodic refresh operations are issued to recharge the capacitor voltage. The interval between refresh commands are referred to as the refresh window. Now let's take a look at this diagram in the context of a RowHammer attack. If enough activations are issued to a nearby row within a refresh window, the charge leakage rate can be accelerated to the point of failure. Subsequent refresh commands now see this bit as a 0 value and maintain the discharge state of the cell. We note that due to manufacturing variation in DRAM circuit elements, different cells are affected by RowHammer at varying degrees. We see that we are able to induce a RowHammer bit flip in the cells represented by the black and blue curves, but not the green curve. I will now discuss the motivation and the goal of our work. The motivation for this study is that denser DRAM chips are more vulnerable to RowHammer. 3 prior works provide RowHammer characterization data on real DRAM chips. However, there is no comprehensive experimental study that demonstrates how the RowHammer vulnerability scales across DRAM types and technology node generations and as DRAM chips become more dense. Therefore, it is hard to identify whether current mitigation mechanisms will remain viable for future DRAM chips that are likely to be more vulnerable to RowHammer. The goal of this work is to first experimentally demonstrate how vulnerable modern DRAM chips are to RowHammer and predict how this vulnerability will scale going forward. And second, we want to study the viability of current mitigation mechanisms on more vulnerable chips. I will now present our experimental methodology for DRAM characterization. We use 3 separate testing infrastructures for each DRAM standard or type that we characterize in this work. We use one FPGA-based soft MC infrastructure for DDR3 chips and another for DDR4 chips. We also use an in-house testing hardware infrastructure to examine LPDDR4 chips. Across our infrastructures, we have fine-grained control over DRAM commands, timing parameters, and temperatures. Below is an example of our FPGA-based DDR4 testing infrastructure. Here we show a table that lists all the DRAM chips that we test. We characterize over 1,500 DRAM chips from 300 DRAM modules, spanning the 3 major DRAM manufacturers, which we anonymize as A, B, and C, of 3 DRAM types or standards, DDR3, DDR4, and LPDDR4. We note that LPDDR4 chips that we test implement on-die ECC. We identified 2 technology nodes per DRAM type, old, new, 1X and 1Y, which we categorize based on manufacturing date, datasheet publication date, purchase date, and characterization results. We define the term type node, which refers to the configuration describing a chip's type and technology node generation. Across the chips we characterize, we identify the 6 DRAM type node configurations listed. To characterize our DRAM chips at worst-case conditions, we take 2 measures. First, we prevent external sources of interference such that the core loop of testing, or the code sequence that repeatedly activates rows, can run consistently as desired and without interruptions. During the core loop of testing, we disable DRAM refresh so that the victim rows are not refreshed during a RowHammer test, DRAM calibration events to minimize variation in test timings, and RowHammer mitigation mechanisms to ensure that we can directly observe circuit-level bit flips such that we can make conclusions about DRAM vulnerability to RowHammer at the circuit technology level rather than at the system level. We also ensure that the core loop of our test runs for shorter than the refresh window to prevent retention failures from interfering with our results. Second, we try to issue the worst-case access sequence for inducing RowHammer bit flips. We construct the worst-case access sequence based on observations from prior work. Using these observations, we test each row's worst-case vulnerability to RowHammer by repeatedly accessing the 2 directly physically adjacent rows as fast as possible. And we refer to our paper for more details on the worst-case access sequence. We describe our RowHammer characterization test using a DRAM diagram and a snippet of pseudocode. To test each row in DRAM, we run the following sequence. First, we set that row as the victim row, in which we will induce RowHammer bit flips. We then set the 2 physically adjacent rows as aggressor rows, which we will repeatedly access. We then disable refresh to prevent interruptions in the core loop of our test from refresh operations. We then refresh the victim row so that we are inducing RowHammer bit flips on a fully charged row and minimizing interference from charge variation in the cells. We then induce RowHammer bit flips in our core test loop by alternating accesses to the aggressor rows. Note that one hammer, which we call HC, refers to 2 accesses, 1 to each of the aggressors. After hammering a prescribed number of times, we then enable DRAM refresh to prevent further retention failures, and we record the resulting RowHammer bit flips for analysis. Finally, we restore the bit flips to their original values, and we repeat this sequence for all rows in the DRAM chip. Now let's go into our characterization results. Before I go into our detailed results, I'll present 3 key takeaways from our experimental characterization study of over 1,500 chips. First, chips of newer DRAM technology nodes are more vulnerable to RowHammer. Second, there are chips today whose weakest cells fail after only 4,800 hammers. Third, chips of newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. The first question we want to answer is, can we induce RowHammer bit flips in all of our DRAM chips? We find that we are able to induce RowHammer bit flips in all chips we test except many DDR3 DRAM chips. We find that of the total set of chips, 84% are vulnerable. The remaining 16% are of DDR3 DRAM types. Within DDR3 old chips, we find only 12% of chips to be vulnerable. Within DDR3 new chips, we find 65% of chips to be vulnerable. We conclude that newer DRAM chips are more vulnerable to RowHammer based on the increasing percentage from DDR3 old to DDR3 new chips, the fact that all other newer chips are vulnerable, and also, as we will show later. In the remaining characterization results, we only show results for chips that we can induce enough RowHammer bit flips in. The second question we want to answer is, are some data patterns more effective in inducing RowHammer bit flips than others? We test several data patterns that are typically examined in prior work to identify the worst-case data pattern for inducing RowHammer bit flips. We find that the worst-case data pattern is consistent across chips of the same manufacturer and DRAM type node configuration, and we use the worst-case data pattern per DRAM chip to characterize each chip at worst-case conditions and minimize the extensive testing time. We refer to our paper for more detail. The third question we want to answer is, how does the hammer count affect the number of bit flips induced? We plot the RowHammer bit flip rate, or the number of observed RowHammer bit flips, to the total number of bits in the tested DRAM rows on the y-axis as a function of the hammer count on the x-axis for DDR4 new chips of manufacturer A as an example. Remember that hammer count is defined as 2 axes, 1 axis to each of the 2 adjacent rows. We plot each of these curves across our DRAM type node configurations per manufacturer. We find that newer DDR4 DRAM technology nodes show a clear trend of increasing RowHammer bit flip rates. The same hammer count value causes an increased RowHammer bit flip rate from DDR4 old to DDR4 new DRAM chips of all DRAM manufacturers. This indicates that RowHammer bit flip rates are increasing with newer technology node generations. The next question we want to answer is, where do RowHammer bit flips occur relative to aggressor rows? We plot the fraction of RowHammer bit flips that occur in a given row offset from the victim row out of all observed RowHammer bit flips for DDR4 old chips of manufacturer A as an example. The aggressor rows at offset 1 and -1 are marked, and the error bars show the standard deviation of the distribution across our tested chips. We find that the number of RowHammer bit flips that occur in a given row decreases as the distance from the victim row, or row 0, increases. This is because row 0 is being hammered from both sides with a double-sided hammer, while rows 2 and -2 are only being hammered from a single side each. We first normalize the data we get across our different chips by inducing a RowHammer bit flip rate of 10 to the -6 in each chip and studying the resulting bit flips. We plot the representative distributions for different DRAM type node configurations ordered from top to bottom. We find that DRAM chips of newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and also farther away from the victim rows. We plot results for each group of chips from each DRAM type node configuration per manufacturer in the paper, and we provide more analysis on these results in the paper. The next question we want to answer is, how are RowHammer bit flips spatially distributed across a chip? We first normalize the data we get across our different chips by inducing a RowHammer bit flip rate of 10 to the -6 in each chip. We plot the distribution of 64-bit words containing X RowHammer bit flips across our tested DRAM chips. We find the proportion of 64-bit words containing X RowHammer bit flips out of all 64-bit words in each chip containing any RowHammer bit flip, and plot the distribution as a bar chart with error bars for each X value. We find that this plot is representative of results from our DDR3 and DDR4 chips. We next plot data that is representative of our LPDDR4 chips. We find that the distribution of RowHammer bit flip density per word changes significantly in LPDDR4 chips compared to other DRAM types. We believe this is due to the interaction of RowHammer bit flips and the on-die ECC that is implemented in the LPDDR4 chips we test. We find that at a bit flip rate of 10 to the -6, a 64-bit word can contain up to 4 bit flips. This indicates that even at this relatively low bit flip rate, a DRAM chip can only be protected from RowHammer bit flips with a very strong ECC code. We show the results for each DRAM type node configuration per manufacturer as is in the paper, and we provide more analysis on these plots in the paper. We next want to answer the question, what is the minimum hammer count required to cause RowHammer bit flips in a chip? We refer to this value as HC first. For each DRAM chip, we find the lowest number of hammers required to induce a RowHammer bit flip in that chip, and we plot the distribution of those values across each chip in a given DRAM type node configuration on the x-axis. We use results from manufacturer C as an example. We plot these distributions as box and whisker plots, where the center line indicates the median, the box edges represent the Q1 and Q3 points, the whiskers extend 1.5 times the difference between Q3 and Q1, and any point outside of the whiskers are outliers and are shown with plus signs. We note the different DRAM types on the x-axis, DDR3, DDR4, and LPDDR4, and subdivide the plots with vertical lines. We focus on trends across chips of the same DRAM type, but different technology node generations to draw conclusions. We plot these distributions across each DRAM manufacturer. We find that newer DRAM chips from a DRAM manufacturer are more vulnerable to RowHammer, which is demonstrated by the clear reduction in HC first values from older to newer DRAM generations across most DRAM types. Across all chips of a DRAM type, we see that HC first reduces significantly from old to new chips. We find that the weakest chip in the latest DRAM type fails after only 4,800 hammers, and we expect this number to decrease further in future chips. To reiterate our 3 key takeaways from experimental characterization, we find that first, chips of newer DRAM technology nodes are more vulnerable to RowHammer. Second, there are chips today whose weakest cells fail after only 4,800 hammers. And third, chips of newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. I will next present our evaluation of mitigation mechanisms after first explaining our evaluation methodology. We use Ramulator, a cycle-level DRAM simulator with a simple core model to examine 48 8-core workload mixes drawn from Spec CPU 2006 with last-level cache misses per kilo instruction, or MPKI values, ranging between 10 and 740. We note that there could be other workloads with which mitigation mechanisms exhibit higher performance overheads, but we did not try to maximize the overhead experience by workload by biasing the workload construction in any way. We use 2 metrics to evaluate our mechanisms. First, we use DRAM bandwidth overhead, which is the fraction of the total system DRAM bandwidth consumption coming from the RowHammer mitigation mechanism. Second, we use normalized system performance, which is the weighted speedup metric normalized to the baseline value, which we denote as 100%. We find that when using RowHammer mitigation mechanisms, most values appear below the baseline, and therefore for clarity we refer to normalized weighted speedup as normalized system performance in our evaluations. While we present the results of both metrics in the paper, we focus on our normalized system performance results in this talk as they are both highly correlated. We evaluate 5 state-of-the-art mitigation mechanisms and 1 ideal refresh-based mitigation mechanism. Please refer to our paper and the respective original publications for more detailed descriptions of each mechanism and how we scale each mechanism to DRAM chips that are more vulnerable to RowHammer or that require a lower hammer count to induce the first RowHammer bit flip in the chip. As a reminder, we refer to this value as HC first. We plot normalized system performance as a function of HC first, or the number of hammers required to induce the first RowHammer bit flip in a chip. A lower Y value corresponds to worse system performance, and we sweep HC first values between 200,000 and 64. We first plot the results for the increased refresh rate mechanism. We note that there is a substantial overhead even at high HC first values, and that it does not scale under HC first values of 32K due to prohibitively high refresh rates required for mitigating RowHammer bit flips. We next plot the results for para and find that it results in reasonable normalized system performance until around the point where HC first is 4,000, at which point the system performance quickly reduces. When HC first is 128, the system suffers 80% performance loss. We next plot ProHit and MR lock for a single data point of HC first equals 2,000. We only plot a single data point since both of these works do not provide models for scaling their mechanisms to lower HC first values, and how to do so is not intuitive. We next plot the results for Twice with the solid line, which has high normalized system performance for HC first values that it supports. In its current form, Twice does not support HC first values under 832K, but we evaluate an ideal version that we refer to as Twice Ideal, assuming that it solves 2 critical design issues in scaling. Twice Ideal is drawn with a dashed line. We note that Twice Ideal has the potential to provide a higher normalized system performance compared to para for all HC first values, but only if it is able to overcome the critical design issues, and we discuss these issues in more detail in the paper. We next plot the ideal refresh-based mitigation mechanism in green. The ideal mechanism works by tracking every single activation and issuing a refresh command to a row only right before it can potentially experience a RowHammer bit flip. We find that the ideal mechanism provides reasonably high normalized system performance across all tested HC first values. However, there is still opportunity for exceeding the scalability of the ideal refresh-based mechanism, which results in 6% performance loss when HC first is 128. We next overlay the lowest HC first values observed across all chips of a given DRAM type node configuration to show exactly how each mechanism would affect a system's performance when used on a system using a particular DRAM type node configuration. We find that para, ProHit, and MR lock are viable options for mitigating RowHammer bit flips in the worst chips that we tested today with reasonable system performance. However, only para's design scales to low HC first values that we are likely to see in future DRAM chips, but has very low normalized system performance. We find that the ideal refresh-based mitigation mechanism is significantly better than any existing mechanism as HC first reduces below 1024. And this indicates significant opportunity for developing a RowHammer solution with low performance overhead that also scales to low HC first values. From our evaluation of mitigation mechanisms, we find that existing RowHammer mitigation mechanisms can prevent RowHammer attacks with reasonable system performance overhead in DRAM chips today. However, existing mitigation mechanisms do not scale well to DRAM chips that are more vulnerable to RowHammer, and there is still significant opportunity for developing a mechanism that is scalable with low overhead. There are additional details in the paper, including a study on the single-cell RowHammer bit flip probability, more details on our data pattern dependent study, an analysis of error-correcting codes in mitigating RowHammer bit flips, additional observations on our data, methodology details for characterizing DRAM, further discussion on comparing data across different infrastructures, and a discussion on scaling each mitigation mechanism. To develop a scalable and low overhead mechanism that can prevent RowHammer bit flips in DRAM chips with a high degree of RowHammer vulnerability, we believe it is essential to explore all possible avenues for RowHammer mitigation. We identified 2 promising directions for new RowHammer solutions. First, we believe that DRAM and systems should cooperate more to provide a holistic approach that can prevent RowHammer at low cost. Second, we believe that a profile-guided approach can provide significant benefits. Accurately profiling RowHammer susceptible cells in DRAM provides a powerful substrate for building targeted RowHammer solutions. For example, in the increasing refresh rate mechanism, the DRAM bandwidth overhead could be reduced by only increasing the refresh rate for rows containing RowHammer susceptible cells. We believe that a fast and accurate profiling mechanism is a key research challenge for developing low overhead and scalable RowHammer solutions. Now that I've presented all of our results, let me conclude. We characterized over 1,500 DRAM chips of different DRAM types, technology nodes, and manufacturers. We studied 5 state-of-the-art RowHammer mitigation mechanisms and an ideal refresh-based mechanism, and we made 2 key observations. First, RowHammer is getting much worse. It takes much fewer hammers to induce RowHammer bit flips in newer chips. And second, existing mitigation mechanisms do not scale to DRAM chips that are more vulnerable to RowHammer. We conclude that it is critical to do more research on RowHammer and develop scalable mitigation mechanisms to prevent RowHammer in future systems. This concludes my talk. Thank you for your time and attention. For many more details, I invite you to read our ISCA 2020 paper.